Okay, welcome to Bonding Review Part 1. So bonding is a pretty long unit, so I've broken it up into 3 different reviews. So this one pretty much covers the different types of bonds, how to draw those bonds, and then a little bit extra about covalent bonding. So first part, why do atoms bond? So atoms bond to become more stable. Ideally, most atoms end up with a full octet. Remember, the word octet means 8 electrons. So when they're bonded, either by transferring or sharing their valence electrons, they should end up with 8, generally. When a chemical reaction occurs, both breaking and forming bonds are often involved. Again, ideally, the new bonds that are formed should be more stable than the ones in the reactants. But this doesn't always happen due to entropy factors. If you remember back in Regents and Honors, we talked about how the spontaneity of a reaction depends on both enthalpy, which is the heat involved, and entropy, which is the randomness or disorder, using Gibbs free energy calculation, which is the delta G. So we're going to look at a diagram on the next page just about the delta H, or the heat involved. So this is a reaction showing nitrogen dioxide breaking up into nitrogen gas and oxygen gas. So if you look at the diagram, remember it's measured by potential energy. The NO2 itself has some potential energy. It's a stable thing. So in order for it to be broken apart, the energy must go up because you have to break those bonds. Ideally, the bonds, again, are stable, so in order to get the atoms out of those bonds, you're going to have to absorb some amount of energy. At the top of that curve is the activated complex. This is the most unstable thing on the diagram. You can tell that because, again, it's the highest amount of potential energy. From the activated complex, when the new bonds are formed, the energy comes back down, and that will always happen. But the relative amount of the energy coming back down is much greater than the energy that was needed to break the NO2 apart. Because of that, the products here are more stable than the reactants, and overall this will be an exothermic reaction. The amount of energy contained in the products is significantly less than the amount of energy contained in the reactants, so they should be considered more stable. On the next page is the second diagram, kind of similar, but this one shows you more specifically the amount of energies involved. So here we're doing a reaction between carbon monoxide and nitrogen dioxide. To break the bonds is going to require 134 kilojoules. Here they show you what they are claiming is the transition state, but I'm pretty sure that's not what's actually going to form there. I don't think that they're all bonded together like that. Could be wrong. But that's going to be your most unstable thing. And then to change your bonds to make your products of carbon dioxide and nitrogen monoxide, you're going to release 360 kilojoules. So the net loss of heat is 226. So you'll see the delta H here is negative, which again indicates that it's an exothermic reaction. There are 3 main types of bonding: ionic, metallic, and covalent. Ionic bonding is when the electrons are transferred from generally a metallic atom to a non-metallic atom, which creates 2 ions, a positive one, a cation, and then a negative one in the anion. Metallic bonding is when metal atoms create an organized structure, and then their loosely held electrons are mobile within that structure. So since they are technically losing their electrons, it's actually an organization of cations that is formed, and then the electrons move around throughout that, allowing it to remain neutral. Covalent bonding is when the electrons are shared between 2 nonmetal atoms, creating a physical bond that actually bonds those 2 atoms together, and they're not allowed to separate from each other. The first one we're going to talk about is ionic bonding. So this, again, generally takes place between a metal and a nonmetal. Metals donate their extra valence electrons to the nonmetals, and they both end up with a total of 8, generally speaking. There is not a physical bond between the ions created, so they are able to separate when they're in polar solvents like water. This whole idea of a physical bond means that those electrons in a covalent bond where they are shared, because they are shared, it's kind of like holding hands. You're stuck together that way. Here, this is like I'm giving you something and you can walk away with it. That's what's happening in ionic bonding. So here there's not a physical bond that holds these things together. Instead, it's just the electrostatic attraction that occurs between the positively charged ion and the negatively charged ion. So while they are very attracted to each other, they are not stuck together. So now we're going to do an example of that. So I'm going to take the element sodium. You'll notice it has 1 valence electron. I'm going to try to make an ionic bond with oxygen, which has 6 valence electrons. And the sodium only has 1 to donate. The oxygen is going to require 2 to reach its stable octet, so we're going to have to add in a second sodium atom. When these things bond, the sodiums are going to lose their electrons and the oxygen is going to pick them up. So what we end up with is 2 plus 1 ions from the sodium, so it's lost its valence electron. It still has 8 in the energy level behind it though, so it's stable. And the oxygen now has 8 in its valence shell and a charge of -2. So here's some practice for you to do. So I'd like you to draw calcium chloride and aluminum nitride. So you need to look up the symbols, find the valence electrons, figure out how many of each thing you're going to need, and then show the final charges. So I'm going to have you pause the video and then try those on your own, and then you can start it again. The answers will be there. Okay, so here's your answers. So calcium chloride, you need 1 calcium, 2 chlorines. So calcium has a +2 charge with no dots now because it gave up its valence electron. Chlorine is going to have a total of 8, so you need 2 chlorines to take the 2 electrons from calcium. So you'll notice I put a little 2 down there at the bottom to indicate there are 2 of them. You could also just draw that out 2 times if you'd rather do that. Aluminum nitride has aluminum with a +3 charge because it had 3 valence electrons. Luckily, nitrogen likes 3 more, so it's going to have just 1 nitrogen with a -3 charge. Here we have some pictures of ionic crystal structures. So I just wanted to point out that usually we draw something that looks like the sodium chloride with the nice organized box-like pattern, but there are a lot of other patterns that the ionic crystals can take, so I wanted to show you a couple examples of those. There's also some examples of these in your textbook as well, so you should take a look at them just to realize that there are other structures you can have. So here I'm going to compare sodium chloride to lithium chloride. Because sodium and lithium are in the same group and they're going to take the same charge, and obviously chlorine is going to take the same charge here, we want to compare their structures. So should they be any different from each other? Well, if you think about it, if you're talking about the arrangement of ions and they're the same charge of ions and the same kind of properties, I would expect them to look pretty much the same, and they do look pretty much the same, so it's that box-like kind of organization there. The same thing is true with other things that have the same kind of charges. They generally kind of take the same structure. Right, properties of ionic substances. So ionic things form crystalline solids at room temperature, which means they're arranged in a 3D repeating pattern. Again, it doesn't have to be that box-like thing. It has to be some pattern that's repeating. The crystals tend to be very hard, and they're very hard because they have such strong electrostatic attractions. So they're held together pretty tightly in terms of the positive ion attracting the negative ion. They have relatively high melting and boiling points, and again, that's because they're so attracted to each other, so it takes a lot of energy to break them away from each other. And they do not conduct when they're in the solid phase, but they can when they're in the molten or liquid phase or when they are in aqueous solution. So why is that? They always contain ions, so you would think they should always be able to conduct. But when those ions are in the solid phase, they are not mobile. They can't move away from each other. But when they're liquid or when they're in aqueous solution, because there's not a physical bond between the 2 ions, simply electrostatic attractions, those ions can move away from each other, which allows them to conduct electricity. So here we have a picture of dissolving in water. Again, because there's not an actual bond between the ions, they can separate and are then able to conduct. They can separate because of the ion's attraction to the water molecules. So here we have polar water. It can pull the crystal apart, surround the different ions with the appropriately charged end of the water molecule, and that kind of keeps them away from each other. Once the ions are separated, now they can carry that charge, so it can conduct electricity. Our next type of bonding we're going to look at is metallic bonding. The next type of bonding we're going to look at is metallic bonding. This takes place between atoms of metals. Because metallic atoms have fairly low ionization energies, which again means it's pretty easy for them to lose their valence electron, their electrons are loosely bound. This allows the metals to form organized structures where their valence electrons become mobile and can flow throughout the resulting metallic cations. The overall charge is neutral, but the electrons are not assigned to a particular metal, meaning they're there within that whole matrix, but they're not assigned to atom number 1 or atom number 2. They can move around throughout there. The sea of mobile electrons allows metals to have some unique and useful properties like malleability, conductivity. Metals are pretty ductile, and they have a luster. If you don't know what those things are, I would highly suggest you look in your textbook and make sure you have a good understanding of what those terms mean. Here's a quick picture of metallic bonding. So we have our cations, because all metals are going to form cations, and then the electrons from those metal atoms are just kind of moving around and they're free. So they can move from place to place within that metallic ion structure. Alright, metallic versus ionic bonding. So both of these types of bonding result in the formation of ions, or an organized structure of ions. But the properties of these substances are pretty different in terms of how they behave under certain conditions. So why are they so different? So here we have a very brief diagram of a metallic crystal and an ionic solid. So which one is which? Well, a metallic crystal must form all cations because they have only cations formed for metals, and it should have some loosely bound electrons. So those are those little dots on the structure on the left. The other structure is the ionic crystal. I can tell because it has both negative and positive ions present. So on the next page we're going to look at what happens when a force is applied to the metallic crystal and a force is applied to the ionic crystal. So that's illustrated by the arrow with the push there. So if I push down on a metallic crystal, the metal is able to change shape, but remain in one piece because the electrons are mobile and they can adjust to whatever change I just applied. So if I pound down on a piece of metal, the electrons are going to adjust to that, and the cations will move around, and you'll be able to change its shape. However, if I push down on an ionic crystal, the crystal is going to experience stress due to the repulsive forces that are created and will break. When I push down on it, you're going to have some negative ions next to other negative ions, and that's not going to work, so the whole thing's going to break apart. If you have a big piece of salt or something and you apply a hammer to it, the salt crystal will break apart because of this. Metallic crystal arrangements, same kind of idea as the ionic crystal arrangements. There's different structures for different metals. Three of them are shown here. There's the cubic body-centered, the cubic face-centered, and the hexagonal. This allows for different densities, different kinds of structures. Again, these are in your textbook as well. I would just look at them so you understand that there's different arrangements for the metallic ions. All right, last but not least, covalent bonding. So there's a lot of information about covalent bonding. In fact, the next two bonding reviews are pretty much all about covalent bonding, so this is the one that's the most complicated. There are two major types of covalent bonding. There is nonpolar covalent bonding. This takes place between two nonmetal atoms that have identical or nearly identical electronegativity values. This allows the electrons to be shared essentially equally and results in a neutral molecule with no dipole moments. So a dipole moment is when you have oppositely charged ends of a molecule or of a bond. Since the electrons are shared equally, that doesn't happen in a nonpolar covalent bond. Polar covalent bonding, on the other hand, is when it takes place between two nonmetal atoms that have different electronegativity values. Electronegativity, if you remember, is the attraction for electrons in a bond. So if they have different electronegativity values, one atom wants the electron more than the other, and so it pulls more on it and is closer, the electrons go closer to that particular atom, which results in that atom having a slightly negative charge and the other atom having a slightly positive charge. So this creates an unequal sharing of electrons, which results in a partial positive and partial negative charge being applied to atoms in the molecule. The atom with the higher electronegativity value will be partially negative. So here we have a little picture of that. So the nonpolar covalent bond. The blue space kind of represents the electron density. So in a nonpolar covalent bond, it's a fairly equal distribution. One end doesn't really have more control of the electrons that are in the bond than the other. However, in a polar covalent bond, you'll notice that one end kind of has more of the electron density. That's going to be the atom with the more electronegative value, a higher electronegativity value. So it will end up with a partial negative charge, while the other end ends up with a partial positive charge. So here we have the review of drawing covalent Lewis structures. So I believe Mrs. Paquette and I both teach the NASU method, so we're going to review that now. Each letter there stands for something. The N stands for needed. So the needed value is either going to be 8 for almost everything or 2 for hydrogen. Remember, needed isn't how many more it needs, it's how many total it needs to reach its stable value. There's some exceptions to this, which we'll go over during class. I just want to let you know there are some, of course, some exceptions. A stands for available. This is how many valence electrons the atom actually has. S stands for shared. Here you're subtracting N minus A. This is the number of electrons that will be shared in the bonds. Since there are always 2 electrons in each bond, to determine the number of bonds, you're going to divide the S number by 2. U stands for unshared. Here you're going to subtract A minus S. This is the number of electrons that are surrounding atoms but not in bonds. So these will be the lone pairs. So we have 3 examples for you to do: water, methane, and carbon dioxide. I'm going to go through water with you and then ask you to do methane and carbon dioxide, and I'll put the answers up after you pause the video. So first, our calculations. So our N number for water is 12. How do we get that number? For hydrogen, you need 2 electrons. Since we have 2 hydrogen atoms, you're going to do 2 times 2. Oxygen is going to need 8, so we have 2 times 2 plus 8, which is a total of 12. For available, hydrogen only has 1 valence electron, so you have 2 times 1 plus the 6 from the oxygen. That's a total of 8. Shared is the difference between N and A, so 12 minus 8, which is equal to 4. And then U is the difference between A and S, so that's 8 minus 4, which is also 4. Okay, now what do you do with those numbers? So we're primarily interested now in the shared number and the unshared number. The shared number gives us the total number of bonds. To figure out the number of bonds, you take the number of shared electrons, which is 4, and you divide it by 2, which gives me 2 bonds. Now, the problem here is I have to figure out how do I put these things together to draw this appropriately. If you can't remember, what you do is find the atom that needs more bonds to reach its stable configuration. So to do that, you look at the available number and compare it to the needed number. So for hydrogen, it has 1, needs 2, so it's going to have to gain 1 more electron, or share to get 1 more electron. Oxygen, on the other hand, has 6, needs 8. It's going to have to share to get 2, so it's the one that's going to go in the center. So you put O in the middle. Now it needs to make a total of 2 bonds. We know that again from our shared number. Since O has to share with 2 hydrogens, it's going to make a single bond with each hydrogen. We also have 4 extra or unshared electrons. Where do they go? Well, hydrogen only wants 2, and when it makes a bond, it has access to 2, so it doesn't want any more. The oxygen wants 8 altogether. It's only making 2 bonds, so it only has access to 4. So those remaining 4 are all going to go onto the oxygen. So when you draw water, it should look like that. So you have your shared electrons with the bond between the O and the H, and you have your unshared electrons as those lone dots up at the top of the O. So if you could take a minute and draw methane and CO2, pause your video, and then I'll put the answers up in a second. Okay, so here is methane. Here's your calculations. Okay, again, C is going to go in the middle because it needs a total of 4 more to reach its stable. And then here's CO2. Again, C is going to go in the middle. It still needs more. This time we're going to make some double bonds, though. Okay. The octet rule. So most atoms in most molecules will reach the desired 8, or octet of electrons through sharing. Some atoms, like hydrogen, lithium, beryllium, and boron, prefer to remain electron deficient, meaning less than 8. We mainly deal with hydrogen of those groups from covalent bonding. So hydrogen, you should really know, only wants 2. Atoms from elements that are in period 3 or higher can accept more than 8 electrons because they have some empty d orbitals, as I'm sure you recall from atomic structure. So for things that need to make exceptions, period 3 and higher can have more than 8. Period 1 and period 2 tend to either have 8 or can take less than 8, but they can never ever take more because they don't have any Ds. There are some molecules that exist in a stable form that do not follow the octet rule. We'll do some examples of those in a second. There are often multiple ways to draw these molecules, but one structure will be the most stable, even if some atoms are not meeting the octet rule. We have 2 tools that we use to help us determine which structure is the best: resonance and formal charge. So resonance. Resonance is when there are multiple possible Lewis electron dot structures for a molecule. This generally happens when there are multiple bond types in the molecules. If you look at the example down below, you'll see that we have both a double bond and a single bond. What happens is resonance is the atoms remain where they are, but the bond shifts around. So here you'll see the double bond started on the right and shifted to the left, and that provides some stability to the molecule because that oxygen with the single bond is not in a good bonding situation, so it's not terribly happy. Because it can trade its stress with the other oxygen, it's a little bit less stressed out. So ideally, resonance kind of works like a group project where everybody actually contributes and helps, and so the overall stress on the molecule should be reduced. The other tool is formal charge. So formal charge is a calculation that you do. The formula for formal charge is valence electrons minus lone electrons minus 1/2 of the shared electrons. So this is the valence electrons the atom actually starts with from the periodic table. The lone electrons is how many lone pair electrons are actually on the atom in the structure it's in. And 1/2 the shared electrons is, remember, for every bond there's 2 electrons, so half of that value should go in there. Okay. In covalently bonded molecules, the atoms in the molecule do not take on their oxidation state charge. So even though we say when we're writing chemical formulas that it has a specific charge, it doesn't actually take a charge because it's not transferring electrons, either gaining or losing, it's sharing, so that's not the same thing. The formal charge is kind of a different way of looking at the charge on a particular atom to help us figure out if the Lewis structure is appropriate. When an atom is assigned a formal charge of 0, the atom is stable. The more zero formal charges that the molecule has, the more stable the Lewis structure will be. If there have to be formal charges, which in some cases there do, typically when you're dealing with an ion, it's better to have any negative formal charges on the more electronegative atoms in the molecule, since those guys want the electrons anyway, so you might as well put them there. For example, we have our sulfate ion. Okay, so when you do the NASU for sulfate, you come up with a structure with all single bonds, and each oxygen has 3 lone pairs of electrons. So remember, when you're doing NASU for an ion, that -2 charge means it has 2 extra electrons available. So the N value is still going to be a total of 5 atoms times 8. For the A value, you're going to have the 6 valence electrons from the sulfur, the 6 for each of the 4 oxygens, and then you're going to have to add 2 extra because of that -2 charge. So just remember, for ions, you have to take those electrons that are there into account. So for negative ions, you're adding to the number of available. For positive ions, you are taking away from the number of electrons that are available. Anyhow, so we have our sulfate drawn here. Each oxygen has a single bond to the sulfur, and each oxygen also has 3 lone pairs of electrons. Everything seems like it should be good because everything has 8 electrons. But when you look at the formal charges, everything has 1. So let's think about how we calculated this. So remember, for formal charge, it's valence electrons minus lone electrons minus 1/2 of shared. So the oxygens all look the same. Oxygen starts with 6 valence electrons. You're going to do 6 minus 6 because it's got those lone electrons, 6 on each one, minus 1/2 of 2 because there's only the 1 bond there. That provides the oxygens all with a -1 formal charge. Sulfur's formal charge, you have 6 valence electrons minus 0 because it doesn't have any lone, minus 1/2 of 8, which is 4. So you have 6 minus 4, which is plus 2. Okay, this is very bad. You do not want a molecule where everything has a formal charge. That's no good. So how are we supposed to fix this, and why is this happening? So there's such a thing as ideal bonding for atoms. If you remember from the atomic unit, atoms typically want to make a certain number of bonds to be in their most stable form. They also have a certain number of lone electrons that they can carry. For example, oxygen has 6 valence electrons. If you look on the periodic table, that's how many it should have. And it would therefore ideally like to make 2 bonds to get up to 8. This leaves it with 4 lone electrons since the other 2 are involved in the bonds. If you think back to when we drew water in this video, that's exactly how the oxygen is. It has 2 bonds and it has 4 lone electrons on it. That's the way it likes to bond. A few other elements that you should know. Hydrogen can really only make 1 bond. It can't make any more than that. because it only has the room in the s orbital. Carbon likes to make 4. It shouldn't ever make more than 4 because it doesn't have room, because again it doesn't have any D's, it only has the S and P. And nitrogen likes to make 3, and oxygen likes to make 2. I added the other group 15 and other group 16 things as well because they like to make those numbers, but once you get beyond period 2, they can take more than that. When elements don't have their ideal bonding situation, they tend to carry formal charges and therefore making the molecule unstable. So if you think back to the diagram we just looked at, all the oxygens in there only make 1 bond. They don't want to make 1 bond, they want to make 2. And they're all carrying 6 valence electrons. They should really only be carrying 4 because they should be making 2 bonds. This makes the oxygens what we would call unhappy. Luckily for us, sulfur is in period 3, so it can exceed the octet rule and can bond like that. So here we have 2 oxygens that are bonding appropriately. They have 2 bonds, they have 4 valence electrons or lone electrons, they're happy. The other 2 oxygens have to kind of stay in their not happy state, so they are only making single bonds and they have a total of 6 lone electrons there. The sulfur itself is making a total of 6 bonds. When you calculate the formal charges here, the only atoms that still have formal charges are the oxygens with the single bonds. So let's just think about that for a second. So now the oxygen with the single bond is the same formal charge calculation we did before, so it's going to be 6 minus 1/2 of 2. The oxygen with the double bond is 6 minus 4 minus 1/2 of 4, which is 0. The sulfur is 6 minus 0 minus 1/2 of 12, so it is also 0. So sulfur is 0, the 2 oxygen double bonds are 0, and the O's that are singly bonded each have a -1 charge, which also sums up to -2, which is good, because that's the charge on the ion. Additionally, because this molecule has 2 different bond types, single and double, it can undergo resonance, which makes it even more stable. So this is a much better structure than the one we came up with NASU. So sometimes you're going to have to adjust your structure based on the formal charges and the ability of resonance. So we know that this is what happens because experimental evidence supports the bonds between S and O's being a 1.5 bond. Now, what does that mean? So because we have resonance, those bonds are constantly moving around. So when you get readings on the bonds, it looks like they're doing a 1.5 because it's a mix of the 1 and the 2. So this further supports the idea of resonance. So in order for us to figure out the best structure, you need to calculate the formal charges for all reasonable Lewis structures, determine which ones exhibit resonance, and then the structure with the most 0 formal charges and the ability to have resonance are usually the best bet, usually. Alright, that's the end of review number 1. We're going to have some practice problems worksheets in class that will focus on this material. I would highly recommend that if you found some of this stuff not familiar, that you take some notes, go back, watch it again. You should also read an outline for your own use, Chapter 8, Sections 1 through 12, and Chapter 10, 10.4, and 10.6, and 10.7. I think that's it. Okay, so we'll see you in class.